Hello, ladies and gentlemen. Welcome to Chapter 1, Day 1. Now that we have completed our sampling and experimentation chapter, Chapter 4, and you've learned how to design studies, now we're going to look at how we can explore the data that is generated by those studies. Remember, in order to infer about a general population, you have to randomly select from a population. In order to determine cause and effect, you need to randomly assign treatments in a well-designed experiment. That's why we started with Chapter 4. In Chapter 1, we're going to start taking a look at the difference between variables and how to start talking about the data that we gather. And so by the end of this lesson, you will be able to identify the individuals and variables in a set of data, classify variables as categorical or quantitative, display categorical data with a bar graph, and decide if it would be appropriate to make a pie chart, and identify what makes some graphs of categorical data deceptive. Now, when we're done with this lesson, this is the book assignment that I suggest that you start working on. We're using the updated 6th edition of the Practice of Statistics. All right, so let's go ahead and get started and dive right in. So 1.1 Day 1, Analyzing Categorical Data. Now for our first question, what is statistics? All right, let's actually lay down what a statistic is. So for our definition, statistics is the science and art of collecting, analyzing, and drawing conclusions from data. All right, this next little bit comes from the overview before Chapter 1. Data are usually numbers, but they're not just numbers. All right, data are numbers with a context. The context engages our knowledge about the world and allows us to make judgments. The context makes the number or word meaningful. If you report a calculation and you don't include the units, if you don't include the context that measurement came from, in other words, the situation that it refers to, then that calculation was completely pointless. It doesn't tell us anything. The whole point of statistics is to be able to analyze and draw conclusions from the data that we collect. Numbers without context don't have any meaning. Right? Now that takes us into how to provide that context. So what is an individual? Do individuals have to be human? And what is a variable? So our first definition, an individual is an object described in a set of data. Individuals can be people, animals, or things. They do not just have to be human. And a variable is an attribute that can take different values for different individuals. So an attribute or a characteristic. Now, the difference between categorical and quantitative variables, what are they? The values of categorical variables are usually words, and the values of quantitative variables are usually numbers. Notice I'm saying usually. Not always, but usually. The main thing that can help you determine whether a variable is categorical or quantitative is whether or not the numerical value makes sense to take an average of. If you're dealing with words, obviously you're not going to take an average of that. But if you're dealing with numbers, is it the type of number that we could find the average amount of? All right, now the general definitions for these, a categorical variable assigns labels that place each individual into a particular group called a category. A quantitative variable takes number values that are quantities, counts, or measurements. Counting up the number of pets you have at home or measuring your height. All right, that's what I mean by counts. When we start talking about frequency, that's going to be the frequency with which a categorical variable appears, or a value of a categorical value appears within a population or within your sample set. All right, so that's going to be a little bit different. So counts can kind of appear in quantitative or categorical, but we use the counting a little differently. Here, the actual data are the counts. With categorical variables, we count up how often a particular data value occurs, all right? Just to kind of fend off any future confusion. Now, do we ever use numbers to describe the values of a categorical variable? Yes. Zip codes are numbers, but they neither count nor measure anything. It wouldn't make sense to take an average of zip codes. All right, zip codes are meant to identify a particular geographic location within a state so that the Postal Service has an easier time delivering things. Now, do we divide the distribution of a quantitative variable into categories? Also, yes. All right, time and age can actually be recorded in intervals, such as 10 to 15 years which would turn a usually quantitative variable into a categorical variable. And an AP exam tip for you. If you learn to distinguish categorical from quantitative variables now, it will pay big rewards later. You are going to be expected to analyze categorical and quantitative variables correctly on the AP exam. And the thing that you need to know is that those two types of variables have different approaches to how we analyze them. Okay, let's go ahead and start taking a look at that. Okay, now, example 1, U.S. Census data. Here is the information about 10 randomly selected U.S. residents from the 2000 census. So as you can see, we have 10 different rows of data. This is just the raw data. Each row represents a different individual. So who are the individuals in this data set? The 10 randomly selected U.S. residents from the 2000 census. For example, the third individual from this census lives in Wisconsin, had 2 family members in their household, is 27 years old, male, married, makes $30,000 per year, and travels 5 minutes to work. All right, so each row provides quite a bit of information about the individual. Each column is a different variable that we have the values of. The different states are values of what state do they live in. The age numbers are different values of the age in years. All right, and that leads us into part B. So what variables are measured, identify each as categorical or quantitative. Now the categorical variables that we have are state, gender, and marital status. While quantitative, number of family members, age in years, total income in dollars, and the travel time to work in minutes. Notice that when there were units of measurement, I included those after the variable to make sure that I was providing a complete context. All 4 of these variables, it would make sense to take an average of. You find the average number of family members, the average age, the average total income, and so on. State, gender, marital status, we would generally look at the frequency with which our sampled individuals live in particular states, what proportion of them were different genders, what proportion of them were married versus never married or single, etc. Now for part C, describe the individual in the first row. In 2000, the individual in the first row was married, female, so it was a married female U.S. resident who lived in Kentucky, had 2 family members, was 61 years old, had a total income of $21,000, and traveled 20 minutes to work. So those are all the details that we know about the individual in the first row. So for quantitative variables, there are 2 different types. So we want to know what the difference between a discrete and a continuous variable are. A quantitative variable that takes a fixed set of possible values with gaps between them is a discrete variable. So that would be things like number of family members. You can't have like 2.5 family members in a household. You'll either have 2 or you'll have 3. We don't count people as partial members. Now, a quantitative variable that can take any value in an interval on the number line is a continuous variable, even if those values are in theory only, with the age that we have listed up here. These ages are in integer values, but someone could be 67 and a half years old, or they could be 21.6 years old, right? They could be any age in between based on how many days, weeks, months, minutes they've been alive beyond the years that they're actually reporting. All right, so most discrete variables result from counting something like the number of family members. There's an error here. Cross out 2020. This was actually 2000. I must have had 2020 on the brain when I was writing this. So in the 2000 census example above. Now, continuous variables typically result from measuring something and are sometimes reported as integer values like age, travel time to work, as I had mentioned. But the possible values are continuous, meaning there are no gaps in theory. So in theory, you could have 20.62 minutes that you have to travel to work, right? Because there are seconds and milliseconds and microseconds in there. Now, we keep talking about distributions. So what is a distribution? The distribution of a variable tells, this should be of, not if. So the distribution of a variable tells us what values the variable takes and how often it takes those values. Now, whether that's quantitative or categorical. Okay, let's take a look at our next page. Something to remember, the values of a variable can be words or numbers. So take a look at these two examples. This is a graphical representation of categorical data, the number of individuals who were married versus the number of individuals who were never married / single. Keep in mind, single could also be people who were married previously but are now divorced, things like that. So that's why there's actually that slash in there. Also notice that there are titles on the axes. We have a consistent scale starting at 0 on the y-axis. On the x-axis, the different values of the categorical variable of marriage status are listed below the bars. Then we have a dot plot. Now we've been making dot plots in chapter 4 as we've been going through our in-class activities. So number of family members, we have our axis titled, we have a clear scale on the number line, and these 3 dots, for example, are the 3 individuals who had 4 family members in their household. We have 3 dots because there were 3 individuals who reported that number. All right, that's the frequency with which that one was occurring. Now, what is the difference between a data table, a frequency table, and a relative frequency table? And which is better to use, when is it better to use relative frequency? So as seen in the US Census data example, a data table lists the individuals in rows and the variables in columns. Remember, each row was a separate individual. Each column showed the value of the variable for that individual in each of those rows respectively. All right. Now, a frequency table shows the number of individuals having each value, the counts. A relative frequency table shows the proportion or percent of individuals having each value. Now, we use relative frequency, proportions, or percents when comparing groups of different sizes. For example, 8 individuals out of a group of 20 is not the same as 8 individuals out of a group of 10. Right? Both are 8 individuals, but one of them is, one of them is about 40%, the other is about 80% of the group that we're looking at. And so the frequencies and relative frequencies listed in tables are not data. If you're asked to provide the raw data, you need to provide me with a data table or a list of the different responses that you received. All right? Frequency and relative frequency tables are not data. The tables summarize the data by telling us how many or what proportion or percent of each response was recorded. So when I ask you for data tables, provide me with the actual data. When I ask you for to analyze them, that's when you can turn them into frequency or relative frequency tables. And now, what is the most important thing to remember when making pie charts and bar graphs? Now remember, a bar graph shows each category as a bar. The heights of the bars show the category frequencies or relative frequencies, while a pie chart shows each category as a slice of the pie, so a slice out of the total, basically. The areas of the slices are proportional to the category frequencies or relative frequencies. That means that you need to know how frequently those values occur in the entire sample group or population group. Whereas a bar graph, you don't necessarily need to know the total frequency with which things occur. And the most important thing to remember, proper labeling, right? Please make sure that you label. Graphs without labels have 0 meaning. They might be pretty, but they don't have meaning. And statisticians prefer bar graphs because they're easier to make and compare, and they can be used when a pie chart cannot. If you're making a pie chart by hand, you actually need to use you essentially have to measure the angle measurements to figure out what proportion or what area of the pie chart is going to relate to each individual section. Bar graphs don't need that. All right, you don't need special tools to make a bar graph. It's the main reason that we prefer it. That's why we say that they're easier to make. Okay, so let's take a look at our last page. So our second example, Arbitron, the rating service for radio audiences, categorizes U.S. radio stations in terms of the kinds of programs they broadcast. The frequency table summarizes the distribution of station formats in a recent year. So we have all these different types of music, types of stations, and then the stations that actually play that type of music. Now, the individuals in the data set who would have been reporting what format of music they play would be the U.S. radio stations. All right, it categorizes U.S. radio stations in terms of the kinds of programs they broadcast. Now, if we make a frequency bar graph of the data, all right, let's go ahead and describe what we see. Now, we have a bar for each one of these formats, including the other category. We have the number of stations along the side. Because we're not comparing two different countries in terms of radio station format, like comparing US to Europe or something like that, we can just stick with the counts, the frequency, so the number of stations. Notice that we're going by consistent scale, by 500s as we're going up, so that we can actually see which format is more common than the others. Now, our description of what we see. On U.S. radio stations, the most frequent formats are the other, so 4852, news, talk, and information stations, 4077, and religious, 3884. Right? The least frequent are the oldies, 831, Spanish language, 878, and contemporary hits, 1012. So when you're describing this, describe what's most frequent, what's least frequent. Since we have so many different types of radio stations here, that's why we're identifying multiple as the highest and multiple as the least frequent. Now there's also a pie chart over here. Because we have this other category, we can actually make a pie chart. And keep in mind, the pie chart must include all categories that make up a whole, which might mean adding that other category. And you can use the pie chart when you want to emphasize each category's relation to the whole. That way you can see which slice is kind of larger than the others. Unless you put the percents along with the labels, it's really hard to tell what proportion of the total they actually are. You can tell which one's larger than the others, but for example, the 19.1%, the 15.3%, the 16%, it's a little difficult to tell which one's actually larger than the other just by the naked eye. So including those percents is really helpful. Now, some common ways to make a misleading graph using icons. So bar widths should be the same. So if you use icons in place of the bars, it can be very misleading. Failing to start the frequency axis at 0, make sure that distorts the actual difference between the bars. If I were to start these right here, then it looks like some are much higher than the others, whereas if you start at 0, you can see the true difference between them. Using 3D effects to make graphs seem more interesting, that distorts the area which our eyes actually react to. All right. Something to note, we need to be careful not to violate the area principle, so area should be proportional to the frequency. Our eyes react to the area of the bars as well as their height, so beware of the pictograph and watch those scales. I love this cartoon here. This is a Dilbert cartoon. Drawn by Scott Adams. It says, I didn't have anything useful to say, so I made this pie chart. And everyone's going, ooh, it must be true because it's pie. It's going, that worked a little too well. I pledged my life and my fortune to the pie. Beware of pie charts. They look pretty. They don't always mean much. All right, and here's your assignment. I'll see you in class.